Okay, so let me kind of remind you what we did last time. And then I'm going to give you kind of a slightly different perspective on one of the examples that we showed. So what we saw was the monotone convergence theorem. So this was our first tool, and a very useful tool, for being able to show convergence of a sequence without actually knowing what the limit was, explicitly. Okay, so this said, if a sequence is monotone, so that just meant increasing or decreasing, okay, then, monotone and bounded, then it is convergent. Okay, and you actually know what the limits are. So in the increasing case, so if we have a sequence AN, it converged to just the supremum of the set AN as thought of as a subset of R, and decreasing, I had this sequence converge to the infimum. Okay. And then we saw an example, so I'll just give you an example where knowing that it converged helped work out what the limit was. So this was example x1 is 2, xn plus 1 is 2 plus 1 over xn. And if we knew it converged, which we were able to work out, so we had x being the limit of xn, we knew that it had to satisfy the equation x is 2 plus 1 over x, and then we were able to solve that x is 1 plus the square root of 2. Okay? So this was, for one thing, that we had to do some work to do this. We also got this other answer, right, which was, I believe x equals 1 minus square root of 2, was a solution to this equation, but not the correct limit. Okay, so we had these cases where you could kind of algebraically find what the limit had to be, except that you might not get the exact right answer. Okay, so I'd like to kind of draw a picture for what's actually going on here. And then we'll see kind of, why this general strategy works and what you have to worry about, okay? So I think I need to make a picture which will be essentially the whole page to try to make it clear. So let me draw this. So what I want to draw is first the graph y equals 2 plus 1 over x, okay? So this looks something like this. And then we have the graph over here. Okay, so there's vertical asymptotes at x equals 0 and horizontal asymptotes at x equals 2. Okay? And then I'm also going to draw the graph y equals x. Okay, so these are my two graphs. All right, and there's 2 points here where the two graphs intersect, right? So there's a point here and a point here. And if you think about it, when you solved this equation, x is 2 plus 1 over x, that's exactly solving to find the points of intersection, where the graph y equals x equals the graph y equals 2 plus 1 over x. So I know exactly what the points are. So the points are, so the intersection points are 1 minus square root of 2, 1 minus square root of 2, and 1 plus square root of 2, 1 plus square root of 2. Okay? And now what we're going to see is that the way that you can kind of think about this sequence of the xn's, so xn plus 1 is 1 plus 2 over, 2 plus 1 over xn, is that you're going to see this by tracing on this graph a certain kind of picture. Okay, so I'll draw what this picture is. So we start at the point x1 is 2. So that means I should be starting somewhere around here, since 1 plus square root of 2 is bigger than 2. Okay? So now let me go up to my graph. Okay, so I trace out my point here. And now you should think about, what is this point? What are the xy coordinates here? Okay? So I know that the point is on my graph, y equals 2 plus 1 over x, and so x is 2. So therefore this point is 2, and then I go to my equation, which is 5/2. Okay? And if you think about it, what this really is that this is my x1 value, and this is my x2 value, right? Because x2 was exactly 2 plus 5/2, or 2 plus 1/2, so I get 5/2. Okay? So I've just gone vertically up. So I start at x2, this is really 2, 0. I go up to my graph and it's 2 5/2. All right, so now you can think I make a vertical move, and now I go make a horizontal move. Okay, so what is this point? Well, again, now we've moved horizontally. So I'm on the point, let's see, so I know that the y value was 5/2, so the y value stays 5/2. But now I'm on the graph y equals x. So I'm at the point 5/2, 5/2. So in other words, I'm at the point x2, x2. Now I go to my graph again. So now where am I? Well, I know my x value is 5/2. My y value, since I'm on the y, again, I'm on this y equals 2 plus 1 over x graph, I get that it's 2 plus 1 over 5/2, which now I'm going to get bad at doing algebra. Let's see, 2 plus 2/5, I believe, which is 12/5. Okay, so let me put that here. Now, actually, the important thing, what it turns out is I don't even really care what the value starts to be. Well, I mean, maybe I care about the value. But what I really care about is that this is the point x2, x3. Okay? Because, again, this is my x2 coordinate. My x3 coordinate I obtain by 2 plus 1 over x2, which I got to be 12/5. And now you see I can keep going in this same way. So I go over here to the y equals x graph. So that gives me x3, x3. I go over here. This is x3, x4, 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 and so on. Okay? So I precisely, what I'm going to end up getting, actually what the picture kind of hopefully shows, is that this convergence kind of spirals until I get exactly to the point where these graphs intersect. Okay? And now you can kind of see what's going to happen if I plug in a different point, right? So I could take a point starting at x is 1. And then I just am going to do this same... I'm going to screw up my beautiful picture, but that's okay. Same picture. You can also check things where x is, -3. Well, it's going to go to -3. Oh, it's going to go up to my graph, then over, and then it just starts going in this spiral again. Okay? So this is a very kind of useful picture. For working out, the values, or I guess the limits of these sequences depending on their initial value. Okay, so it's not, if I go back to, let me zoom back out. Remember, if I go here, it wasn't necessarily obvious that I had to, that I had to converge to this one and not this one. I mean, in this case, I had a positive versus a negative, so I was able to kind of easily check. But you can imagine there's other functions where this becomes hard to work out, but this picture kind of is a good guide, at least, right? You can start drawing on the graph, draw y equals x, plug in your point, and see where it kind of ends up going, okay? So maybe I'll just mention kind of another kind of additional topic, which is, I mean, it's essentially the same picture, but incredibly interesting and useful, it turns out, in biology. So this is a very simple graph. This is just, you draw gamma x times 1 over x, and it turns out this is some real number where you have to make it, I think, between 0 and 4. Okay, I kind of forget. Okay, and then you draw the line y equals x, and you play the exact same game as you did before. Okay, so you go up to your graph, and over, and up, and over, down, over. And now you might think, well, the same thing happens, you just automatically spiral towards maybe that point. Turns out to not be always the case. So I'm just going to refer to Wikipedia, because they'll draw better pictures and have better information than me. So this is called the logistic map. And it turns out that you get kind of very different behavior for depending on what the value of this lambda has to be. Okay, so in some cases it just kind of converges towards this point. In other cases you have much more chaotic behavior. So this comes up in population models. Again, I'm going to refer to Wikipedia for, more information. Okay? Okay, so that was a little aside. Though really the first is just a very useful way to think about these sequences. So now let me kind of go back to where we were with the monotone convergence theorem. Okay? So let me say, keeping up with our theme of zooming in on the real line. So we've seen this in kind of a couple different ways, right? We had the nested interval property, which let us zoom into R, or now we're starting to look at sequences. It turns out to be useful to extract a subsequence out of a given sequence. Okay, so let me give you an example, and then we'll talk about it. Okay. So the example is the sequence 0, 1, 0, 1, 0, 1, and so on. This is kind of the easiest sequence which does not converge. Okay, because, well, it's easy to check that, if you, basically the only limit options are 0 and 1, and since it's fluctuating, you'll never get arbitrarily close to 1 for all n, or arbitrarily close to 0 for all n. On the other hand, this is really, missing, just saying, oh, this sequence does not converge, is really missing some information, right? Because there's really two convergent sequences in this inside, right? Okay, so first, if I look at just the terms which are odd, that just get 0, 0, 0, and so on. And if I look at the terms that are even, I'm getting 1, 1, 1. Okay? So I have two convergent sequences. The problem is, the reason that it's not convergent is that the two sequences are converging to two different places, right? So one sequence goes to 0, one sequence is going to 1. All right? So we want to if we want to really understand a sequence, we like to understand, how these, all of its subsequences, how these are converging and diverging. Okay? So let me give you just the formal definition of a subsequence. So let xn be a sequence, and let n1 less than n2 less than nk, and so on, be a strictly increasing sequence of natural numbers. Okay, so I could just say I want an infinite subset of the natural numbers. And that naturally has this ordering. Okay. Natural numbers. Then I just am going to define a new sequence as x sub n k is just xn1, xn2, xn3, and so on. Okay? So the kth term of this sequence, of the subsequence, is the n sub kth term of the original sequence. Okay? And kind of the power here is that there is a lot of flexibility here, right? So that if you have a sequence, there are a lot of subsequences of it. So there's kind of a lot of information here. Okay? So this is called a subsequence of the xn's. Okay? So let me just do one example. So if xn is 1 over n, so I get 1, a half, a third, and so on. Well, of course, I can look at sequences that look like a half, a fourth, a sixth, and so on. Okay, so this is just 1 over 2k. Or I could get, 1, a half, a third, a fifth, a seventh, 1 over prime for p prime. Okay, there's just complete flexibility in what a sequence can be. In particular, I don't need to know at all what a formula is for the x sub n sub k. So, sometimes you get it for free, like this is really just x sub 2k, but you can imagine just taking a totally random subsequence, and that's perfectly good. Okay? So let me give you kind of the first basic fact, which is useful to know, which is if you have a convergent sequence, so if the xn's do converge to x, then the x sub n sub k's also must converge to x. Okay, so let me do the proof. Okay. What you should think about is, what this is saying is every term is eventually within epsilon of x for any epsilon. Okay. Well, since this is a subsequence, this is going to occur too. Okay, so you just have to be a little careful with the numbers. So let me just say let epsilon greater than 0. By convergence, there exists some n in n, so that xn minus x is less than epsilon for all n bigger than or equal to n. Okay? So since n sub k, let me just put this here, is an infinite sequence, there is some k so that, maybe I'll make this capital K, so that n sub k is greater than n. Okay? So in particular, all of the terms after that are also bigger than n. So therefore, for k greater than or equal to k, x sub n sub k minus x is less than epsilon, since n sub k is greater than n. Okay, so the only tricky part here is that you have to, the x sub n's are indexed by the naturals. The n sub k's are indexed by the naturals as well, but it's indexed by k rather than n. Okay, so that's just, again, it doesn't really change the idea of any of the proofs, but the write-up you have to be a little careful. Okay, so we can use this, it turns out, to characterize divergence. To characterize divergence of a sequence. Okay, which is something that we've really been focused on proving things that converge, right? And we just say, when do they diverge? When are they not converging to something? So here's a theorem. So let xn be a sequence. Okay. We're going to assume, well, let me just put it this way. So the following are equivalent. The first is that xn, I'll write it like this, does not converge to x. Okay. So the second one is there exists some epsilon not greater than 0, so that for all k in n, there exists some n sub k in n, so that n sub k is greater than or equal to k, and x n k minus x is greater than this epsilon 0. Or the other way to say it is, well, there exists some epsilon not greater than 0 and a subsequence x sub nk of xn, so that x sub nk minus x is greater than or equal to epsilon naught. Okay, for all k and n. Okay, so what is this saying? I mean, so the first, 1 implies 2, is just doing a careful negation of the statement xn goes to x. All right, so this I'm really going to just encourage people to write out themselves. I told you what it ends up looking like, but write down the statement for convergence and then go through and negate it, okay, by making all of the less than epsilons into greater than or equal to epsilons and so on, okay, all of the for alls into there exists, okay? So 2 implies 3 is really just choosing the right subsequence. So choose the subsequence that 2 gives you. Okay, so in other words, maybe I'll just draw this picture. So if I have x, what 2 is saying is like there is some epsilon so that however far I go into the sequence, so maybe here, if I go k out, no matter how far I go, there's going to be some x sub n sub k, which is farther than epsilon naught. Okay? And then the subsequence, it just comes from looking at this x sub n sub k. Okay, so what we're saying is there are infinitely many terms which are farther away from this x plus epsilon naught. Notice that there are also some terms, like we have no idea where x sub n sub k plus 1 is, right? It could very well be within epsilon. But then if you go further out, there's going to be another one, which is even further. Okay, so this is supposed to be n sub k plus 1. And this would be n sub k plus 1. Okay, that's slightly confusing. Okay. But what I'm saying is we don't know, there could be many terms that are very close to x, but we know that there have to be these terms, if it doesn't converge, that are far away. And then the subsequence just says, look at it far away. Okay? And then finally, 3 implies 1 is the same idea. If you have this subsequence which stays far away from x, then that's going to that's going to stop you from converging, right? Because you just choose epsilon now, which is smaller than that distance. Okay, so let me give you some more criteria. So this is called divergence criteria. Okay, so what has to happen? So suppose that xn is divergent. Okay, so there's no x which it converges to. Well, there's two possibilities. Okay? Then either it has two convergent subsequences, which converge to different points. Okay, so you could think the sequence 0, 1, 0, 1, and so on is an example of that, or it's unbounded. Okay, so I have the sequence just 1, 2, 3, 4. So this is pretty remarkable criterion. Okay, it's saying that these are kind of the only possible ways that a sequence can misbehave and not converge to a real number, right? You can either have something which just bounces between, and they therefore have convergent sequences that converge to separate things. So maybe I should say I did the same example. I could also look at, like, say, 1, a third, 2/3, a quarter, 3/4, a fifth. I'm not sure why I changed my numbers here, a fifth, a fourth, and so on. Okay, so this is supposed to be, you can check, there's this convergent sequence here, which goes to 0, and a convergent sequence here, which goes to 1. Okay? So it doesn't have to be exactly, 0, 1, 0, 1, 0, 1. You can have more varying behavior. Okay? And that's it. Okay, so either it's unbounded, so it just shoots off, or you have this. Okay, so here's, let me give you an exercise, which is kind of a hard exercise. Show that sine of n is divergent, okay, using this criterion. Okay, so this turns out to be tricky, but in general you should think that this is kind of generally, it's a great criterion, but it's hard to apply okay? Because you have to find the subsequences. Okay, so usually if you're just given a sequence, it's pretty easy to work out whether it's bounded or not. Just seeing whether the numbers go up to infinity. What's trickier is, actually finding these two subsequences which converge to different things. Okay? So in some sense, it's no harder or no easier than showing that a sequence is convergent. Okay. Okay, so I'd like to end just by showing, a pretty major theorem, actually. But so it turns out to be, at least for us, going to be the most useful fact about subsequences. Okay, so again, if we want to find subsequences, we want to find nice subsequences. Okay, if you're given some arbitrary sequence, you'd like to find something which is nicer, and then you hope to understand it. Okay, and what we're going to do is try to find monotone subsequences, because these are things that we kind of know by the monotone convergence theorem. So here's monotone subsequence theorem, which is if xn is a sequence, then it has a monotone subsequence. Okay, so it turns out that this just works. So let me write x sub n sub k. All right, so this will be very useful for us, since we know at least that there's some subsequence which we can start to understand. Okay, so let me tell you the proof. Okay, so I'm going to just give a word for something. Okay, so we're going to say that xm is a peak if x sub m is greater than or equal to x sub n for all n greater than or equal to m. Okay, so it's bigger than all future terms. Okay, so let me give you kind of the picture here. So it's useful to start thinking of this actually as a function from n to r. So these are going to be my points in my sequence. Looks something like this. And what it's saying is if x3 is a peak, okay, then I know that for any other term in my sequence, it has to be less than or equal to x3. Okay, so it's below this line. All right, and I don't have any idea what's going on. It might even go up and reach the peak at some point, but this is not allowed. Okay, so I will undo it. Okay, so this is saying x3 is a peak if we get a picture like this. Okay, and now there's going to be two possibilities for our sequence. So there's two possibilities. So the first is you have this sequence that you're interested in, and there's infinitely many peaks. Okay, so I'll draw, again, some sort of picture. You have the x sub, which I'm going to call it first peak x sub n1, second peak x sub n2, and so on. Again, I don't really know what they look like at all, but I know they have to be decreasing, or at least not increasing. Okay? And I know this because, well, each one of these is a peak. It's bigger than every single term. Okay? So therefore, you just list the peaks. So the subsequence that you get is listing the peaks. We said there's infinitely many of them, so this is okay. And so what you get is like x sub n1, x sub m2. Oh, for some reason I switched to m's. Sorry. Okay, where this is a peak, so therefore x sub n1 in particular is bigger than x sub m2, since it's bigger than every single term, bigger than x sub m3, and so on. Okay, so what you get is a monotone decreasing sequence. Okay, so what's the other possibility? Well, the other possibility is only finitely many peaks. Okay, so the sequence, oh, so let me just say, so then we're done, right? I've constructed for you, oh, sorry, this is a subsequence. I've constructed for you what we want, right? So this sequence of peaks is a decreasing subsequence. Notice I didn't say anything about it being bounded or whatever, right? So this might go to minus infinity. I don't care. Okay? So the other one is that xn has finitely many peaks, right? That's the only other possibility. Okay? So let's say that x sub, m1 up through x sub mk are the peaks. So we've listed them. So every n bigger than mk has x sub n not a peak. Okay? So eventually there's no more peaks. So you're climbing this mountain, and well, so what you can think of is if you're climbing the mountain, here's you, right? You know that you're going downhill, right? In this case, you know that you're always going to be moving uphill, right? Because eventually, you have things that are never, because there's always something bigger in your future, okay? There should be a nice motto for life based on that, I guess. So now let's go there, okay? So let's just say x sub, I want to change my number again. So I'm going to say x sub t1 is greater, is my first sequence with t1 greater than m sub k. Okay, I just want to choose something large enough out here so that this is not a peak. Okay, not peak. Okay, well, what does it mean to not be a peak? Okay, it means that there's some term in its future, which I'm going to call t2, which is strictly larger, right? So x sub t2 has to be, there has to be some t2 which is larger than x sub t1 for some t2. Otherwise, x sub t1 would be a peak, but, there's only finitely many of those. All right, and now, rinse and repeat. X sub t2 has to be less than x sub t3 for some t3. Again, otherwise, x sub t2 would be a peak. But we've gone far enough so that there's no more peaks. Okay, so here's x sub t2, x sub t1. I keep going. This isn't a peak, so I have to find some x sub t3, which is even larger, and that's your subsequence. Big, rinse and repeat. Okay, so in particular we have x sub t1, x sub t2, x sub t3, and so on, where the x sub t, say sub k plus 1, is chosen so that x sub tk is not a peak. Okay, so being not a peak guarantees you this existence of this t sub k plus 1, so therefore you get a monotone increasing subsequence. Okay? So if you have infinitely many peaks, you get a monotone decreasing thing. If you have finitely many peaks, you get monotone increasing. Either way, we're happy. Okay? So we will, I'm going to stop here since this was, I think, already pretty long. So I guess on Wednesday, or the thing that I'm planning for Wednesday, it's going to be practice midterm. So after next midterm, we'll see many more applications of this. Okay. Graphs intersect.